So today we're going to continue our discussion of momentum. So far we've defined momentum, right? Mass times velocity, and something called an impulse, which is the force applied for a certain amount of time to change the object's momentum. Today we're going to look at the topic of the conservation of momentum. So let's look at our objectives. The first is we'll explain the law of conservation of momentum of an object. And then second, we'll look at two types of collisions, an elastic and inelastic. And then we'll be able to solve some problems around conservation of momentum for these two different types of collisions or interactions between objects. So let's jump right to the definition of the law of conservation of momentum. In the absence of an external force, the momentum of an object or system of objects is unchanged. In other words, the momentum before a system has some type of interaction has to be equal to the momentum after the interaction if there is no external force. Now, it may sound a little bit similar, right, to Newton's first law in the absence of an external force, but let's see what it looks like in real life. So the important part of this is we have to define what makes up the system of objects when we apply the law of conservation of momentum. So let's look at an example here. We've got three billiard balls or pool table balls, and we're going to have some interaction between the balls. Okay, now the first question is momentum conserved if the system includes only the 11 and the 14 balls? Okay, now let me put in motion here what the interaction looks like. Here's our system, right? Just the 11 and the 14 ball. So the 13 ball comes, it hits the other two, right? And then they continue on. So think about it. What was the momentum of the system before the collision, right? The 11 and the 14 ball were at rest. They had no momentum. After the collision, when the 13 ball hits them, they now had velocity. So they now did have momentum. So they went from zero momentum to some amount of momentum, right? To positive momentum to the right. So since the momentum changed, we'd say no, the conservation was not conserved. Momentum before was not equal to momentum after. Why is that? Well, the 13 ball, since it was not part of the system, provided an external force. Now let's redraw the system to include the 13 ball. So when it rolls and collides with the other two, now we see that the momentum of the system was equal to that of the 13 ball before the collision. And then after the collision, that momentum was transferred to the 11 and the 14 ball. So the momentum before in the 13 ball was equal to the momentum after in the other two balls. And we would say that momentum is conserved. Okay, so it's really important how we define the system. What objects are within the system? What objects do we consider to be external to the system? All right, let's look at some other cases here. So if we have a cannonball and cannon, and we define the system only as the cannonball, would momentum be conserved? Okay, now before we fire the cannon, right, both the cannonball and the cannon are at rest. Momentum would be zero. But once we fire the cannonball, right, the cannon goes to the right slowly, and the cannonball goes to the left quickly, right? So they both have momentum. But if it was only the cannon ball that was part of the system, right, it had zero momentum before and then had a large amount of momentum after, right? So we'd say momentum is not conserved. Now, what if we make the entire thing the system, right? The cannon and the cannonball, so that when we fire the cannon, the ball goes to the left with its momentum, the cannon goes to the right with its momentum. They would have equal and opposite momentum. So the net sum would be zero. So the momentum before we fire is zero, and the momentum of the system after we fire is zero. Okay, so we would say in that case, momentum is conserved. The cannon ball and the cannon have equal but opposite momentum after firing. Okay, so it's very important again to define what we mean by the system. All right, let's look at the two different types of collisions. The first is what we call an elastic. This is when objects collide without being permanently deformed or without generating heat, and momentum is conserved between the two objects. Often we think about these collisions when the objects basically bounce or rebound off of each other. Okay, so let's look at a simple example, right? A hits B, transfers its momentum to B. That would be an example of an elastic collision. If we were to think about law of conservation, the momentum before has to be equal to the momentum after. Well, what makes up the momentum? We have, remember, P stands for momentum. So the momentum of ball A plus the momentum of ball B before the collision has to be equal to their momentum after the collision. Now, in practical terms, right, in this example, ball B was not moving before the collision. So all the momentum was just in ball A. So we can put 0 in for the momentum of B. After the collision, it flips, right? The momentum of the ball A is now 0. So we can put that in our equation. And ball B has all the momentum. So if we apply the law of conservation of momentum, basically we can say that the momentum of A before the collision is equal to the momentum of B after the collision. Now you're going to see this same setup of this equation, right? Momentum before equals momentum after in each of the cases that we look at and the problems we'll be working on. All right, let's look at one other case here. Two balls are going to have the same mass and velocity, but moving towards each other. And as they do that, they bounce off and go in the opposite direction at the same velocity. Okay, so again, was momentum conserved? Yes, but here's where we need to pay attention to the vector quantities of momentum, right? It has both magnitude and direction. So if we call to the right as positive and to the left as negative, right, we see that momentum of ball A was positive. Momentum of ball B was negative before the collision. And then after the collision, they rebound in opposite directions. So the ball A now has negative momentum and ball B has positive momentum, okay? So ball A and B have equal and opposite momentum before and after the collision, and momentum is conserved. The other type of collision we can have is what we call inelastic. Okay, so this is when objects collide and become entangled or coupled together. And we're still going to assume that momentum is conserved. Okay, so let's look at the case here, back to the beginning where ball A has momentum and ball B is at rest. So this time when they hit, right, they lock together and then continue on. Now, what would that look like in terms of our equation, right? So before the collision, momentum is all in ball A, ball B is at rest, and then afterwards, you could say they share the same momentum because they're locked together as if they were a single object. So how do we show that? Well, here it is, momentum of the ball A plus 0, remember ball B was at rest before the collision, is now equal to the momentum of A and B together. Or we could say the momentum of the ball A has to be equal to the momentum of the two of them together after the collision. Okay, so here's an example of inelastic collision. All right, what happens if they both come together but at different speeds? Well, we saw, let's back that up and look at it one more time here. Ball A will have greater velocity than B, but they have the same mass. So the net momentum is going to be to the right. Okay, so once they collide and lock together, they're going to continue moving to the right. So we can set up our equation again here, right? We had the same momentum of A and B together after the collision is equal to their individual momentum before the collision. And again, we've got to be careful that we have the correct sign of which way the objects are moving as we include the direction of the momentum, not just its magnitude. All right, let's look through a few examples with some actual numbers here, okay? So we have car 1 with a mass of 10,000 kilograms and a velocity of 20 meters per second collide with car 2. It has the same mass and they're resting on ice, so there's no friction. After the collision, car number 1 has 0 velocity. So first, what type of collision do we have? And what is the speed of car number 2 after the collision? Now, you could probably predict this, right? Let's do our collision here. So car 1 hits car 2, car 1 comes to a stop, and car 2 continues on. So they bounced off of each other. So the type of collision is a elastic collision. Now, what would the speed of car number 2 be? Well, think about it. If they have the exact same mass, that means they're going to have the same momentum before as after. And if they have the same mass, therefore the velocity of car 2 has to be the same after. It would also be 20 meters per second. But let's put our equation together and see how that works. We should always be able to get that same result. So here's our 4 different momentums, right, of car 1 and 2 before and car 1 and 2 after. So we know car 1 has a momentum of 1,000 times 20, right, mass times velocity. Car 2 had 0 velocity, right, so that's going to basically be 0 momentum. Car 1 after had 0 velocity, and then car 2, that's the velocity that we're trying to solve for. Okay, so it looks like kind of a messy equation, but look what happens, right? These terms are 0, and we're simply left with 20,000 kilogram meters per second equals 1,000 kilograms times the velocity. And if we divide by 1,000, right, we get what we expected. It's going to have the same velocity as the first car did because they have equal mass and they are having an elastic collision with no loss in energy. All right, let's try it again here. Okay, same thing, but now notice car number 2 has half of the mass, 500 kilograms. So again, we have an elastic collision. They bounce off of each other. And let's set up the equations now, the same thing we did before, right? But notice we have 500 kilograms as the mass of car number 2. Now, again, these 2 of these terms drop out because they have 0 momentum before for car 1 or car 2, and car 1 has 0 momentum after. So here's our new equation to solve. If we divide by 500, notice we now get 40 meters per second. So since the mass of the second car had half that of car 1, right, 500 versus 1,000, then in order for it to have the same momentum, it's going to have twice the velocity. So it goes from 20 to 40. All right, let's look at one more example here. 2 identical cars. This time, their collision is going to be an inelastic collision, right? They lock or tangle together. So what is the speed of the 2 cars after the collision? Well, again, let's start with our mass or momentum before and after. Prior to the collision, they each had their own momentum. After the collision, notice how I write the equation now. Since we're treating them like a single object locked together, I'm going to add their masses, mass 1 and mass 2 of the 2 cars together times their common or shared velocity. So let's put some numbers in here, right? We've got 1,000 times 20 for car 1. Car 2 is 0 velocity. And then we'll add their masses together after times the unknown velocity. Now, you might be able to make a prediction here, right? If they lock together, now their mass basically is twice of what the moving car was before, then their velocity would have to be half in order to have the same momentum. So let's see if the equation gives us that, right? This term goes to 0. So we're left with 20,000 kilogram meters per second for the momentum before equals 2,000 kilograms, right? The combined mass times our unknown velocity. So if we just divide by 2,000, we get 10 meters per second, which is what we predicted, right? If we affect double the mass of the system that has momentum, In order for the momentum to be the same, we have to have half of the velocity. So it drops from 20 to 10. All right, that's it. So we've learned what the law of conservation of momentum of an object means. And we know that there are two types of cases, right? Elastic, where they bounce off of each other, and inelastic, where they couple together and act as one object.